In this video, we're going to start Chapter 1 of the geometry textbook. So Chapter 1 is on line and angle relationships, and it makes sense that in a course in geometry, we're going to start with defining what exactly a line is, what exactly an angle is, and look at what the different ways line and angles are related. Relationships between angles and lines are going to be at the foundation of the majority, if not all, of what we study in this entire course. Okay, but the opening section in this chapter, the opening section to the entire textbook, is on sets, statements, and reasoning. Okay, so here's the opening page for the chapter, line and angle relationships. It says, magical. In geometry, figures can be conceived to create an illusion. Known as the Bridge of Aspiration, this passageway was conceptualized by the Wilkinson-Eyre architects. It connects the Royal Opera House and the Royal Ballet School in Covent Garden in London, England. In this geometric design, 23 square portals are each rotated slightly in order to create the illusion of a twisted passage. Although a visual inspection of the bridge might have one think that people would have to walk on walls to cross Floral Street below, it is easy to walk upright. The architectural design successfully creates the fluidity, grace, and spirit of the dance. This chapter opens with a discussion of the types of reasoning: intuition, induction, and deduction. Additional topics found in Chapter 1 and useful for design include tools of geometry such as the ruler, protractor, and compass. By considering relationships between lines and angles, the remainder of the chapter begins the logical development of geometry. For the geometry student needing an algebra review, several topics are found in the appendix. Other topics are developed as needed. So yeah, when it comes to the algebra, there's a full algebra course on the channel, so go check that out. If there's some concepts that come up that you need to review, go scroll through the geometry playlist or the algebra playlist and watch what you need. And so, yeah, I mean, this is more of architecture, and it's a series of, squares that are slightly, each one is slightly rotated relative to the previous. And I'm assuming they've got, this is just like there's no load on this on these squares here. There's a beam's going across and you just walk straight across. But yeah, I mean, that's, there's geometrical shapes that you would use in architecture. Here's an arc, a circular arc. Here's another circular arc. Here's a geometrical shape. So all these have their own areas, volumes, etc. So, you could think about calculating what is the volume of this entire piece here. We probably have to use calculus for that, but to set up the calculus formulas, you would have to understand geometry, the basic underlying geometry principles. So, okay, but as it says, though, in this chapter, we open with a discussion of the types of reasoning: intuition, induction, and deduction. And then additional topics found in this chapter and useful for design include tools of geometry, such as the ruler, the protractor, and the compass. By considering the relationships between lines and angles, the remainder of the chapter begins the logical development of geometry. Yes, so we're going to start geometry by considering the relationships between lines and angles. That's the natural starting point. Okay, so it opens with describing what a set is. And we talk about sets at the start of algebra. And in the algebra course, I kind of looked at sets as sort of mathy. I didn't want to get into it too much. I felt like, since, again, this is not for math majors, this channel, but, I guess sets are kind of good to know, even for non-math majors, to understand what they are, because we do use the term a good bit in math, and it's really simple. It's just a math term for like a group. You can take, if there's anything that you want to, any group of numbers, anything you want to put in its own group for the sake of discussion, for the sake of a problem, for the sake of a proof, whatever, you want to put it in its own category, its own group. In math, you call that a set. That's it. You can make anything a set. You can make up your own set. You can do whatever you want. So it says it's a collection of objects. A set is a collection of objects, all of which are known as the elements of the set. Okay, so you can make anything a set. Here, this is, if you look at this here, that's the set of, this is a set of 3 numbers, 1, 2, and 3. That's it. And they say, okay, they say A is the set of elements 1, 2, and 3. I mean, you could technically make anything a set of baseballs, a set of, you could, anything, you can say a set of anything. But I guess in math, it's typically usually numbers, but not always. So don't overthink this. A set is anything that you want, no matter, and you can define it to be whatever you want, absolutely whatever you want. You can make up any set that you want. And all you're doing is, for the sake of a problem or a proof or something, you're putting these elements of the set, whether it be numbers or whatever, just into their own group for the sake of the analysis of the problem. You might compare this set, A, to another set. Okay, so that's why they call, the different types of numbers. There's the set of real numbers, the set of imaginary numbers. But then you can make there's subsets of the real numbers. Now, what's a subset versus a set? Subsets are just sets. It's just in the context you say the word subset. Subset is just a term you use if the context of what you're talking about means, for the sake of like communicating it, you want to say subset. So when I say subset, I'm saying that subsets of real numbers, I'm saying that there's sets that are every one of a subset of real numbers means that every element in all the subsets is a real number. So the subsets of real numbers are the integers, the whole numbers, the rational numbers. Those are all subsets of real numbers. But if I took, 5 minus 1, 0, 3. This is a set of 4 numbers. I just made this up. This is a set. And it's 4 integers. So it's a subset of the integer set, which the integer set is a subset of the real number set. So that's the idea. And I can name this set H for Aberry Engineering, whatever. Okay? And the idea of union and intersection, that's for comparing sets. So if you say that set A union set B, that means everything in A and everything in B. That's what you're saying. You might specify this for communication. You might say, okay, we have 2 sets, which can be absolutely anything. You could do this with the set of integers and the set of rational numbers. I'll say integers union rational numbers. That's not the correct variables, but just saying that's all integers and all rational numbers is what you're saying. Now, if you say intersection, you're saying you do this. You're saying just everything that's both in A and B. So like from the perspective of a Venn diagram, if you had set A and set B, union means all of this. Intersection means just this. So if you said the set of, the set of integers intersected with the set of rational numbers, which would mean any ratio of integers, intersection. Integers intersected with rational numbers, what would that mean? Well, we know that you can have rational numbers can be like 3/5. There's a ratio of integers, but even integers are rational numbers. So like 2 over 1, that's a rational number. And so actually it would be, if this is all rational numbers, every single integer is a rational number. So that means the integer set is a subset of rational numbers. So the I intersection with R would be, if this is I, this is R, would be this. But there might be a case with like the subset of real numbers, all the subsets of real numbers, that they'd be separated and you'd have to do like this. There's like a crossover. But again, it could be a set, like a clearly defined set, like the set of real numbers, imaginary numbers, or the set of whole numbers, or it could be a set you just make up. that's completely arbitrary for a specific problem. All right. Now, let's see. So in geometry, geometric figures such as lines and angles are actually sets of points. Yeah, so a line, in a plane or in 3D or whatever, that's a set of points, right? You could look at it that way. It's like an infinite number of points, but it's a set. You could say something like, I don't know the official math notation here, but the set of all numbers on y is equal to x plus 1, where x is any real number. So you take x being any real number and you put it, it's the set of, or you'd say ordered pair, something like that, but you could define a set as a set of all points on a line. So, there's an official way you could do that. And use that for comparison. You could say that set in union with another set or intersection with another set. If you had 2 points in a plane or 2 lines in a plane and they crossed, if you said the set of all points on this line A intersecting with the set of all points on this line B, that set would contain 1 point. So again, if you define a set as all points on line B and another set as all points on line A, and you did A, well, let's say union B, then that would be all these points and all these points. If you said A intersection B, that would be just that 1 point. That's because only that point is in both sets at the same time. Okay. They talk about subsets. So, yeah, here's another symbol. We didn't learn this in algebra, but this symbol, so we know union and intersection. We know union and intersection, but you can say this to indicate subset. So the set of integers, is that right? Yeah. The set of integers is a subset of the rational numbers. These symbols are incorrect for integers and rational numbers, but that's true though. But you couldn't say the set of rational numbers is a subset of integers. That's not right. Okay, so there's a symbol for subset. So it says in chapter 2, we will discover that all triangles, so the set of all triangles, you can say the set of all triangles that exist in the universe, of any triangle. You can that's just a made-up set, but you can say that. That is a subset of polygons, because every single triangle is a polygon. Every single triangle is, by definition, a polygon. But not every polygon is a triangle. Like a square, that's a polygon. That's not a triangle, though. You see? Okay. Now, statements. A statement is a set of words and or symbols that collectively make a claim that can be classified as true or false. Okay, so a statement is not something you're not going to write. It's not a rule or like a something that you can rely on, like an official, something you wouldn't take a statement and put it on the back cover of a textbook. In general, you wouldn't do that, because it's not a statement is just it's like what it says, you're making a statement. But it's not just, you can't just string a random sentence together and call that a statement in the math sense. A statement is something you've kind of officially put on the chopping block. It has enough words and symbols, and it's a claim about something that it makes enough sense to where it can officially be classified by you or other people as true or false. Like I can say a triangle has 4 sides. That's a statement. Now that's not true, but that is a statement though. And people can come in and critique that statement and prove it true or false. Okay, so again, it's definitely not just, you can't just say anything that anybody says is a statement. It needs to have enough information to where, okay, it's officially kind of on the chopping block. So here's some examples of statements. 4 plus 3 is equal to 7. That's a statement, right? I could also say 5 minus 2 is equal to 1. That's a statement. Okay, this is a true statement. An angle has 2 sides. That is a true statement. Robert E. Lee played shortstop for the Yankees. That's a statement, right? But it's like you could be talking to your friend and you can think about statements that you make with your friend all the time, that he or she makes or you make. But it's not like everything that ever comes out of your mouth is a statement, right? It needs to have enough. It's like you've laid it out there. Once you've like officially laid something out there, then it becomes a statement where it can officially be argued about. Then it becomes a statement. Like if you say Robert E. Lee played shortstop for the Yankees, now you've opened up the door for conversation. That's a statement. 7 is less than 3. That's a statement. That's false. The Robert E. Lee statement is false. Here we go. Look out. That's a great example. Look out. What is that? Is that a statement? No, it's not a statement. Because you can't debate about it. I guess that's the idea. It's something that has to be debatable. Okay? Some statements contain one or more variables. A variable is a letter that represents a number. Okay, so yeah, there's statements that involve variables. Not every statement involves a variable. Robert E. Lee played shortstop for the Yankees. That doesn't involve a variable. Okay, what is a variable? It's a letter that represents a number. That's what a variable is. In math, a variable, it's a letter that represents a number. The claim x plus 5 is equal to 6 is called an open sentence or open statement because it can be classified as true or false, depending on the replacement value of x. Okay, so yeah, if you're given the statement x plus 5 is equal to 6, that's an open statement because it depends on the variable. You have to pick it depends. You can't, it's not officially a statement, right? It's an open statement because you can't, just like as this sits, you can't say if it's true or false or not until you give more information. But it's still kind of a statement because it's one tiny step away from being a statement. So it's an open sentence or open statement because it can be classified as true or false depending on the replacement value of x. For instance, x plus 5 is equal to 6 is true if x is equal to 1. For x not equal to 1, it's false. Some statements containing variables are classified as true because they are true for all replacements. Consider the commutative property of addition, usually stated in the form a plus b is equal to b plus a. In words, this property states that the same result is obtained when two numbers are added in either order. For instance, when a is equal to 4, b is equal to 7, then it follows that 4 plus 7 is equal to 7 plus 4. Yeah, so these, they're not saying it here, but this is called an identity. But the difference here is that this is like a property. And so this is true, that the essence of a property is it's true for any number A and any number B. So this is a statement because this is true. This isn't true depending on some condition or some variable you pick. This is true as it sits. So this is not an open statement. This is a statement. The negation of a given statement, P, makes a claim opposite that of the original statement. So they're giving a statement of variable, P, and a negation makes a claim opposite that of the original statement. If the given statement is true, its negation is false, and vice versa. If P is a statement, we use this curly symbol here, which is read not P, to indicate its negation. This means not. Okay, give the negation of each statement. So 4 plus 3 is equal to 7. That's a statement. So we want to write something that claims the opposite of this statement. That would be the negation. We're going to write another statement. A negation is another statement. That is the opposite of a certain statement. So if they're saying that 4 plus 3 is equal to 7, well, we can say that, 4 plus 3 is not equal to 7. It's the counter argument is what it is. All fish can swim. Well, what's the counter to that? No, all fish can't swim. So like, in other words, this is saying that all fish can swim. So we're saying, no, that's not true. All fish can't swim. I can find a fish something that's classified as a fish that can't swim. That would negate that statement. Okay. A compound statement is formed by combining other statements used as building blocks. In such cases, we may use letters such as P and Q to represent simple statements. For example, the letter P may refer to the statement 4 plus 3 is equal to 7, and the letter Q to the statement Babe Ruth was a U.S. president. The statement 4 plus 3 is equal to 7 and Babe Ruth was a U.S. president has the form P and Q and is known as the conjunction of P and Q. Okay? The statement 4 plus 3 is equal to 7 or Babe Ruth was a U.S. president has the form P or Q and is known as the disjunction of statement P and statement Q. A conjunction is true only when P and Q are both true. A disjunction is false only when P and Q are both false. Okay, yeah. It's kind of like a compound inequality. You have compound and inequalities and compound or inequalities. You can take more than one statement. I'm assuming you can do this for not just two, but two or more, but we're just starting with two here. And you can combine them together. And they give statements variables. And the conjunction, the combination, like you have a situation where both for the it's like you're making one, you're combining two statements into one statement, to where for the whole statement to be true, you need two like kind of sub-statements to be true, both of them. That means the conjunction is true. Or you can combine two statements to say that if either one of those statements are true, just or, then you call it the disjunction, that is true. Okay. Assume that statement P and statement Q are both true. Okay. So there's two statements that give them variables. Classify the following statements as true or false. 4 plus 3 is not equal to 7, and an angle has two sides. False. That's a conjunction of P and Q. That's false. No, because that's not true. However, 4 plus 3 is not equal to 7, or an angle has two sides. That's a disjunction of P and Q, and then that's true. Okay. The statement if P then Q, known as a conditional statement or implication, okay, if P then Q is a conditional statement or implication, is classified as true or false as a whole. So you look at this as a, kind of like we had two statements combined to make a conjunction or disjunction. Here you have two statements combined to make a conditional statement or an implication. And then just like with this conjunction or disjunction, you could classify the whole conjunction or disjunction as true or false as a unit. Same here. You can classify an entire implication or conditional statement as true or false as a whole. A statement of this form can be written in equivalent forms. For instance, the conditional statement, if an angle is a right angle, then it measures 90 degrees, is equivalent to the statement, all right angles measure 90 degrees. Okay, so first here they're giving an example of a conditional statement. If an angle is a right angle, then it measures 90 degrees. So the first statement is, okay, an angle is a right angle. That is, that's a statement, right? You could make a statement, angle theta here is a right angle. Is that statement true or false? Okay, let's say it's true. So the first statement P is true. Okay, well then in that case, it's going to be true that that angle is going to measure 90 degrees. If this statement is true, then you can make another statement, the angle measure is 90 degrees. That's automatically going to be true. If the first statement is true, then that means that the next statement is automatically going to be true. That's a conditional statement or an implication. And it's saying you can rewrite conditional statements in different equivalent forms. So you could say that if an angle is a right angle, then it measures 90 degrees. You could write that as all right angles measure 90 degrees. That's what you're saying, right? This statement, if an angle is a right angle, then it measures 90 degrees, is saying that any right angle is going to measure 90 degrees. All right angles are 90 degrees in measure. Okay, classify each conditional statement as true or false. If an animal is a fish, then it can swim. I mean, I guess that's true. So if you have I have an animal and I make a statement, it's a fish. If that statement is proven true, then automatically the next statement, you don't even have to think about it. The next statement is saying that animal can swim. That is true automatically. Is that true? Well, I mean, I think that's true. Okay. Yeah, that's stating all fish can swim. If two sides of a triangle are equal in length, then two angles of the triangle are equal in measure. But yeah, that's a conditional statement. So, well, I mean, we haven't studied that yet, but that's good. It's interesting to think about. If you have a triangle, you make the statement that two sides are equivalent in length. and that turns out to be true, then that automatically means that there's going to have two angles are going to be equal in measure. I believe that's true. If Wendell studies, then he will receive an A on the test. No, that's not true. Just because Wendell studies doesn't mean that he automatically will receive an A on the test. Okay, so if we come here, statements 1 and 2 are true. Statement 3 is false. Wendell may study yet not receive an A. That's right. In the conditional statement, if P then Q, P is the hypothesis and Q is the conclusion. Okay, so in a conditional statement, the opening statement is the hypothesis and Q is the conclusion. In statement 2 of example 4, we have the hypothesis. Two sides of a triangle are equal in length. The conclusion is that two angles of the triangle are equal in measure. So that's another way of looking at the term hypothesis. It's the opening term in a conditional statement, which is kind of confusing to me because when I think hypothesis, I think of an official scientific statement in a way. Well, no, I wouldn't say that, because with these statements, you can state something that's explicitly false. A hypothesis is, you've collected data. The data seems to suggest that there's a truth there. And so you make a hypothesis that, okay, this looks to be true. The data says that this statement here is true. But then, but that's just, you've just opened the door to questioning. Now you have to do more investigating, test it more. So it's kind of confusing to me in that they're saying these conditional statements are the opening statement is a hypothesis, but again, that's just another way of looking at the definition of hypothesis. Conclusion makes sense. That's the conclusion of the conditional statement. For the true statement, if P then Q, the hypothetical situation described in P implies the conclusion described in Q. This type of statement is often used in reasoning. So we turn our attention to this matter. So, okay, let's look at this, what they said here, this statement. For the true statement, if P then Q, the hypothetical situation described in P. So that's more of what they're using the term hypothesis for. In a conditional statement, the opening statement introduces a hypothetical. If this is the case, in other words, hypothetically, if you had a triangle where two sides of the triangle are equal in length, hypothetically, then the conclusion is that there's going to be two angles of the triangle that are going to be equal in measure. So that's how they're using the term hypothesis here. And I think for a scientific method, I guess you would say a hypothesis is like a hypothetical. If you're doing a scientific experiment and you make a hypothesis, is that hypothetical? I don't think so, but that's the way they're using it here. Okay, so the hypothetical situation that the opening statement describes implies the conclusion described in the concluding statement. Okay, so then again, it said, this type of statement is often used in reasoning, so we turn our attention to this matter. Okay, so now reasoning. We've talked about sets, statements, now reasoning. Success in the study of geometry requires vocabulary development, attention to detail and order, supporting claims, and thinking. Reasoning is a process based on experience and principles that allows one to arrive at a conclusion. The following types of reasoning are used to develop mathematical principles. So intuition, induction, and deduction. So yeah, you've heard of inductive reasoning, deductive reasoning. So, okay. Intuition is an inspiration leading to the statement of a theory. Induction is an organized effort to test and validate the theory. And deduction is a formal argument that proves the tested theory. Okay, yeah, so intuition, your intuition, your experience, and your observations combined together, it kind of gives you an inspiration to make a statement, a strong statement. Induction is an organized effort to test and validate a theory. So it's more of it's not just you're making a strong intuitive statement. It's like induction is now you've maybe made an intuitive statement and now you're going to go through a systematic process for testing the theory, the statement that you made. Deduction is a formal argument that proves the tested theory. So yeah, after you've done testing with induction, now you can come up with a deduction that's like making a formal argument that proves the tested theory. So, okay, let's go through these, though, in more detail. Intuition. We are often inspired to think and say, it occurs to me that, that's right. With intuition, a sudden insight allows one to make a statement without applying any formal reasoning. When intuition is used, we sometimes err by jumping to conclusions. In a cartoon, the character having the bright idea using intuition is shown with a light bulb next to her or his head. Figure 1.3 is called a regular pentagon because its 5 sides have equal lengths and its 5 interior angles have equal measures. Okay, so it's all 5 sides have equal lengths and all the interior angles have equal measures. So it's called a regular pentagon. What do you suspect is true of the lengths of the dashed parts of lines from B to E and from B to D? All right, so the length of B to E and B to D are equal. That's what my intuition tells me. And where does that come from? I don't know, just the symmetry of this. Intuition suggests that the lengths of the dashed parts of lines, known as diagonals of the pentagon, are the same. Okay, so that's what your intuition tells you. You didn't, there's no, just your experience and your common sense made you make a statement. Okay, now using induction and a ruler, we can verify that this claim is true. So induction is you're going to say, all right, I'm going to make more of an organized effort to prove this. You know, I just kind of proved it. I made kind of a deductive argument when I said that the symmetry of this would suggest that the fact that it's a regular pentagon and these lines are like symmetric about the line of symmetry of this pentagon, that's a pretty good deductive statement, honestly. But still, though, induction is we're making like a systematic effort to prove that statement. So they're saying you use a ruler and you measure. Okay. And then now using methods found in chapter 3, we could use deduction to prove that the 2 diagonals do indeed have the same length. So you can actually make more of a formal argument that states definitively that, like, to me, you could measure this with a ruler, each of these, and then you could use deduction to write a formal argument saying these 2 lines have equal length because I measured them, right? Like, but that's kind of I mean, that's a deductive reasoning, but that's kind of silly because then you want to make more of a statement about why the diagonals of this pentagon are equal in length. So just saying you measured them doesn't prove anything. So that the induction, the organized effort to figure out why 2 diagonals like this of a regular pentagon are equal, you need to do more than just use a ruler. Maybe the ruler could help to validate your intuitive statement to then validate you going down a deeper path to actually prove it, going down, doing more inductive reasoning, more induction to eventually come up with a formal deductive argument that you can write on paper and say, this is true. The diagonals of a regular pentagon are equal in length. The role intuition plays in formulating mathematical thoughts is truly significant, but to have an idea is not enough. Testing a theory may lead to a revision of the theory or even to its total rejection. If a theory stands up to testing, it moves one step closer to becoming mathematical law. So yeah, if you have an intuitive statement, sometimes your intuition is off. It happens all the time, even if you have a lot of experience. So what's going to happen is the theory you made with your intuitive statement is going to need to be tested with induction. And then if it holds up, then it can eventually become mathematical law. Okay, induction. Let's take a closer look at the meaning of induction. We often use specific observations and experiments to draw a general conclusion. This type of reasoning is called induction. As you would expect, the observation experimentation process is common in laboratory and clinical settings. Chemists, physicists, doctors, psychologists, weather forecasters, and many others use collected data as a basis for drawing conclusions. In our study of geometry, the inductive process generally has us use the ruler or the protractor. The protractor is for measuring angles, and then the ruler, obviously, lengths. Okay, while in a grocery store, you examine several 6-ounce cartons of yogurt. Although the flavors and brands differ, each carton is priced at 75 cents. What do you conclude? So yeah, I mean, this is a really simple example, but the idea is this process of examining the cartons, they're trying to illustrate that as inductive reasoning. You're doing an investigation. So think about it. Of the three types of reasoning, you could have intuition, induction, or deduction. Well, this isn't intuition. Whenever you're examining the cartons, that's not, you're doing some investigating. You might have used your intuition to make a statement prior to doing the investigating of what the yogurt's going to cost. Then you do some investigating, which is inductive reasoning, and then you make a conclusion. You say every 6-ounce carton of yogurt in the store costs 75 cents. Just if it's a 6-ounce carton of yogurt, doesn't matter the brand, they just price them all the same. Or the flavor, just price them all the same. Okay, as you may already know, see figure 1.2, a figure with 3 straight sides is called a triangle. Figure 1.2 was this. Yeah, so I think everyone pretty much has heard of a triangle. If it's any figure within a plane. So just to illustrate this, if we think about 3D space, okay, this is 3D space. You have like an X direction, a Y direction, a Z direction. You can draw a plane oriented anywhere in 3D space. We typically think of, I guess you would say the YZ plane. I mean, it doesn't have to be the YZ plane, but like your computer screen or a piece of paper is the YZ plane or the XZ plane or the XY plane, but you could draw a plane oriented anywhere in 3D space. Okay, and within a plane, you can draw a triangle. It's any figure that has 3 sides. That's a triangle. Doesn't matter what the side lengths are, whatever. 3 sides, it's a triangle. Okay, in a geometry class, you have been asked to measure the 3 interior angles of each triangle in this figure. You discover that triangles 1, 2, and 4 have 2 angles as marked that have equal measures. What do you conclude? What may you conclude? So, okay, here are these triangles. These angles within these triangles have equal measures. And so by the measuring process, you're doing deductive reasoning. It's just any kind of investigation. You could think of like they just mentioned in a lab, physics lab, chemistry lab, biology lab, engineering lab, whatever. That's what's going on is inductive reasoning, investigations, data, observations. Okay, now, so you would conclude that the triangles that have 2 sides of equal length also have 2 angles of equal measure. So I'm not sure how would you know this? You haven't taken geometry, so I'm not sure you measure side lengths did you measure you used a protractor to measure the interior angles, and you saw that some of the triangles had 2 equal interior angles, and so you make the conclusion that they're going to have at least 2 equal side lengths. So, well, how would you know that? But yeah, I mean, that's the idea. You can do inductive reasoning, do investigations with measurements, etc., and then make concluding statements based on that induction process. Now, these concluding statements and these last 2 examples, to me, I guess you would consider that more of intuition. In the context of how they stated these, that you're more of making an intuitive statement. You could have made an intuitive statement prior to doing the inductive investigation, inductive reasoning. You could have made, again, with the yogurt, you could have given your assumption of what the yogurt's going to cost based on your intuition. You do some investigation, you measure the angles of the triangles, then you could make another intuitive statement that's kind of giving a conclusion. But if you want to make an official statement, an official argument that serves as sort of like a proof of something, that's what deduction is. So, I mean, I guess I'm not sure what a mathematician would say. Maybe you could say that this is deduction. I guess you could say that this is deduction. You're making an official statement, but I guess I'm not thinking that this is deduction because you haven't stated any of the reasons why this is true. Every 6-ounce carton of yogurt in the store costs 75 cents. There's no backing. You just for this statement. And so if we come to deduction, so deduction is the type of reasoning in which the knowledge and acceptance of selected assumptions guarantee the truth of a particular conclusion. Okay, reading that definition, I guess this would be deduction. You could make an intuitive statement prior to inspecting the cartons of yogurt about what you think it's going to cost, that they're going to cost. But in the context of you've done the investigation, you've seen the price of the different cartons, and so you now make an official statement that every 6-ounce carton of yogurt in the store costs 75 cents. You're basing that off of facts that you've gathered with inductive reasoning. You've done the inspection, you've gathered the data. Now you're making a statement that's backed by these facts. You're making another statement of fact. Here, you've done an induction process measuring the angles of triangles, and I guess I'm assuming that they, based on the previous example problems, that if you have two or more angles of a triangle that are equal, then you know that at least two sides are going to be equal. So based on your inductive investigation, inductive reasoning with these triangles that have equal angles, then you can make this deductive statement that's saying that the triangles that have two sides of equal length also have two angles of equal measure. That's backed by the knowledge that you already, the facts that you already know that are already accepted about triangles with equal angle measures having equal side length measures. Okay, so again, deduction is the type of reasoning in which the knowledge and acceptance of selected assumptions guarantee the truth of a particular conclusion. So let's read this slowly here. You see what it's saying? It's the type of reasoning. It's a reasoning in which you can state a fact about something. You can state, you can guarantee the truth of a statement by first backing it with knowledge that's already accepted as true. You're backing something with knowledge and statements that are already accepted to be fact to guarantee the truth of a conclusion you're making. And you see how this is different than intuitive reasoning. It's subtly different in that your intuition, you could make a statement of intuition, and it's, usually if you're experienced that statement's it's a true statement, but it doesn't it might not be true. You're kind of brainstorming. With intuition, you're brainstorming. You might be wrong. But with deduction, you're saying, you're kind of signing on the dotted line. You're saying, no. I am stating something that I am not wrong here, because of this, here's with the backing of these first 2 or 3 or whatever statements, I'm going to make this statement. And that is so, and that statement I make is a fact. I'm guaranteeing it's a fact. That's more of deductive reasoning. Whereas, like inductive reasoning is more of investigative, observations, data collection. Okay, so more about deduction. So in example 8, we illustrate a valid argument, a form of deductive reasoning used frequently in the development of geometry. In this form, at least 2 statements are treated as facts. These assumptions are called the premises of the argument. On the basis of the premises, a particular conclusion must follow. This form of deduction is called the law of detachment. Okay, so notice it says at least 2 statements, so you can have more than one kind of backing statements, and those statements are treated as facts. Those are called the premises of the argument, and on the basis of those premises, you can then state a conclusion that you're trying to guarantee is true. Now, if you think about it, to try and understand what this meaning of deduction, etc., you do this all the time. We do this all the time. If you're having an argument with somebody, you do this all the time. If you're trying to convince someone of something or trying to argue with someone about something, and you're about to state something that's you believe is indisputably true. You're arguing with your friend, whoever. A typical way you do this is you start with some facts that you feel are fact, and that your friend or whoever also feels is fact, and really the the society as a whole would already agree is fact. It's hot in the summer. That's a fact. There's no one's going to really argue with that, right? So you might open with that. That might be one of your reasoning, one of your backing statements. Your friend would agree. Of course, it's hot in the summer. We agree with that. That's a fact. You state some other premises, and then on the basis of those premises, you state what you're trying to argue is fact. Your conclusion about something. Okay. So this is doing it this way. This is just one form of deduction. It's called a valid argument, and this form of deduction is called the law of detachment. So there's other forms of deductive reasoning, but this is one form, one method of deduction. Okay. So let's look at an example here. If you accept the following statements, that the following statements 1 and 2 are true, what must you conclude? Okay. If a student plays on the Rockville High School boys varsity basketball team, then he is a talented athlete. Yeah, so, okay, one way you can think about this is, okay, is it when we're saying is this a fact or not? I mean, it depends on the context. I mean, if you're arguing with a judge, or you're just talking to a friend of yours, I guess this would be like saying, there's some high school basketball teams that you have to be like going to be drafted into the NBA to play on those teams, like the IMG Academy in Florida. You can make a statement in an argument that's saying, look, if somebody plays on IMG Academy's basketball team, then they're a talented basketball player. If we're talking in the context of relative to other high school basketball players around the country. Again, it depends on the context of the argument, but you could say that. So the first statement, if a student plays on we'll say IMG Academy boys varsity basketball team, then he is a talented athlete. Okay. Your friend would say, of course. I agree. Everyone knows that. It's like saying if someone plays football in the NFL, they must be good at football. Of course. Okay, now the second statement, Todd plays on the, I'm going to say IMG Academy boys varsity basketball team. So the conclusion is Todd is a talented athlete. Okay, so yeah, that's the argument. If someone was saying Todd isn't a good basketball player, if you're at a typical high school and you're just talking about just basic basketball, and someone's saying that this player is no good at basketball, he's better at basketball than this guy, and you're saying, I'm going to convince you that this guy's a good basketball player, would you agree that anyone that plays on the IMG Academy boys varsity basketball team, he's a talented athlete? Everyone agrees with that. Okay, of course. Well, this guy he's a starter on that team. So that means he's a talented basketball player, a talented athlete. You've won the argument. That's the deductive reasoning technique of the law of detachment. This is a valid argument, and this form of deduction is called the law of detachment. So to more easily recognize this pattern for deductive reasoning, we use letters to represent statements in the following generalization. So here's the law. Here's what we just did, laid out with symbols. The law of detachment. So let P and Q represent simple statements and assume that statements 1 and 2 are true. Then a valid argument having conclusion C has the form. So really, if we think about this, there was 2 general statements here that were being used. 2 general statements. We were saying that the first statement was, a student, someone plays on this basketball team. That's not a guarantee. You have to first ask the question, is someone a starter on IMG Academy's varsity basketball team? So that's the first simple statement. A certain student is a starter on the IMG Academy basketball team. That's the first statement. The second statement is based on a person is a talented athlete. So it started with the first statement was a conditional statement. So if a person plays on the IMG Academy basketball team, then the person is a talented athlete. This is kind of stated in general. Okay, then we kind of reused statement P, but we're more specific this time, saying that Todd plays on the IMG Academy basketball team. So they're calling P the same statement, but we were just more specific in statement 2. We made Todd the student. Well, the conclusion then is that, and then they match up here. Todd is a talented athlete. Okay, so let's see. That's the law of detachment. So let's see if we can recognize this pattern in the next example. So let's see. In the preceding form, the statement, if P then Q, is often read P implies Q. That is, when P is known to be true, Q must follow. Yeah, that's like the essence of a conditional statement. So, okay, is the following argument valid? Assume that premises 1 and 2 are true. Okay. If it is raining, then Tim will stay in the house. Okay, and then statement 2 is it is raining, right? So the P here is the statement of is it raining or not? They're going to use it is raining. That's the P. It's raining. The statement, it is raining outside. Okay, so P implies Q. Statement P implies statement Q. If it is raining, then Tim will stay in the house. So this is the first full, it's a conditional statement that contains 2 simple statements, right? That's what every conditional statement is, a combination of 2 statements. Then statement 2 is, well, it's raining. That's where these match up. It's raining, so Tim will stay in the house. That's true. It's valid. Okay, let's look at another example. We're going to assume these premises are true. If a man lives in London, then he lives in England. Okay, the first statement is a man lives in London, and that's combined into a conditional statement with a man lives in England. So if statement Q is true, that implies the truth of statement, or if the statement P is true, that implies the truth of statement Q. Okay, well, then the second statement is a man, we're going to be more specific, William lives in England, so therefore, or wait. No, they said this is not going to be true because the pattern is for the law of detachment. The next statement is going to be based on the condition, the opening conditional part, the hypothesis, the hypothetical. So for the law of detachment, the second statement should be based on the hypothetical. Okay, well, William lives in London. Therefore, William lives in England. But no, they're doing it. They're saying, okay, well, William lives in England, which this is based on the conclusion of the conditional statement. But that's not what we learned was the pattern of the law of attachment. So saying that William lives in London, no, that's not necessarily true. So it's not valid. Okay, to represent a valid argument, the law of detachment would require that the first statement has the form if Q, then P. Even though statement Q is true, it does not enable us to draw a valid conclusion about P. Of course, if William lives in England, he might live in London, but he might instead live in Liverpool, Manchester, Coventry, etc. Each of these possibilities is a counterexample disproving the validity of the argument. Remember that deductive reasoning is concerned with reaching conclusions that must be true, given the truth of the premises. So you can't, there should be no counterexample that disproves the deductive argument. Okay, so but let's make sure we understand this. For this case, we would require if Q, then P, because we're stating that William lives in London. To use the law of detachment here, the valid argument method for deductive reasoning, we need the second statement to be based on the hypothetical of the first conditional statement. And why is that? Because with the conditional statement, we're saying if this is true, then that implies something else is true. We're saying that the first statement, the hypothetical, if that is true, that's going to guarantee the truth of the conclusion. And so with that, then we're going to make the second statement is going to be saying, okay, well, look, here's a situation where here's the hypothetical, right? That's the idea. Where the second statement's going to be like a offshoot of the hypothetical. So then you can say, well, there you go then. So since the conditional statement is a true statement, then we can say William lives in London. But you can't use the conclusion though of the conditional statement, the opening conditional statement for the second statement, because it's not the case with a conditional statement. It's not necessarily the case that if you have if P then Q, it's not necessarily the case that if Q then P. It might be, but not necessarily. So yeah, it could be true. Like if you have 12 eggs, then you have a carton. Okay, flip that. If you have a carton of eggs, then you have 12 eggs. That works. But, here's a good example. If a man lives in London, then he lives in England. Okay, if a man lives in England, does he live in London? Well, no, that's not necessarily true. So with a valid argument, the law of detachment, you need the second statement to be an offshoot, just like you're maybe being more specific or whatnot, of the hypothetical statement of the opening conditional statement. Okay, so that's what they show here. Valid argument. If P then Q, then here's that's the opening conditional statement. Then the second statement is based on P. Conclusion is based on Q. But invalid is if P then Q, then you make the second statement Q and make a conclusion about P. Not necessarily, because we know conditional statements you can't necessarily flip them and it'd be true. Sometimes that's not true. We will use deductive reasoning throughout our work in geometry. For example, suppose that you know these two facts. If an angle is a right angle, then it measures 90 degrees. Angle A is a right angle. So angle A must be 90 degrees. And actually this, you could flip this and it's still true. If an angle measures 90 degrees, then it's a right angle. In this case, you can flip it. But if they're saying it's still improper, it's not correct to write, if an angle is a right angle, then it measures 90 degrees, angle A measures 90 degrees, then you would conclude that it's a right angle. That is true, but you haven't written that correctly, though, per the law of detachment. You want to put the second statement should be based on the hypothetical. Okay, because the form found in statements 1 and 2 matches the form of the valid argument, you may draw the following conclusion. Angle A measures 90 degrees. Yeah. So, I guess you could do it to where you put the conclusion as part of the conclusion of the conditional statement as part of the second statement, but you might need to include another premise. The following conditional statement can be flipped. So I don't know what the technical word for that is, but it's valid in both directions. And then you say, okay, with that, if an angle is a right angle, then it measures 90 degrees. Angle A measures 90 degrees. Then it's a right angle. Okay, well then that works. But that's not the way we're going to look at it. When we use deductive reasoning, when we use the valid argument, we're going to do it to where the second statement is based on the hypothetical of the opening conditional statement. All right, Venn diagrams. Sets of objects are often represented by geometric figures known as Venn diagrams. Their creator, John Venn, was an Englishman who lived from 1834 to 1923. In a Venn diagram, each set is represented by a closed bounded figure, such as a circle or rectangle. So yeah, Venn diagram, you could use rectangles. If statements P and Q of the conditional statement, if P then Q, are represented by sets of objects, P and Q respectively, then the law of detachment can be justified by a geometric argument. When a Venn diagram is used to represent the statement if P then Q, it is absolutely necessary that circle P lies in circle Q. That is, P is a subset of Q. So, okay, yeah, so just note that with a Venn diagram, what you're doing is, with Venn diagrams, you're representing sets of numbers, objects, whatever, and the relationship between sets. That's what you're doing with a Venn diagram. And so each set is going to be represented by a closed figure, a bounded figure like a circle or a rectangle. But we typically see circles. But now they're going to actually use this with these statements. So that's not really sets. I guess a statement is not a set. So they're going to use it a different way here. So, okay, here's the valid argument. If P, then Q. So if P is true, then that means Q is also true. That's like saying if something is in set P, then it must be in set Q. 100%. This has to be fully in set Q. But you see, you can't flip this. You can't say if something is in set Q, then it must be in set P, because look, you see? Now, the idea of when you could flip the conditional statement, then you can think about that as the circles would be the exact same size, and they would be the centers would be they'd be lying right on top of each other. So if P then Q, or if Q then P. And then let's see. So yeah, I'm not sure what this figure 1.6 would come into play with this example. So use Venn diagrams to verify example 8. So let B equal the students on the Rockville High varsity basketball team. Let A be the people who are talented athletes. So B is people on the team. A is all talented athletes. And so, yeah, set B, which is anyone that's on the, I'm going to say, IMG Academy basketball team. Okay, well, all of the talented basketball players in the country, you have talented players that aren't on that IMG basketball team, right? But everyone that's on the IMG basketball team is within a talented athlete. So they're all in set A. Set B is entirely in set A. It's a subset of set A. Okay, but then Tom is a part of set B. So that means Tom is within set A. If Tom is in set B and B is a subset of set A, where A is all talented athletes and then B is people on the team, well, then Tom is in set A. He's in set B. That means he's also in set A as well. Okay, the statement, if P then Q, is sometimes expressed in the form all P are Q. For instance, the conditional statement of examples 8 and 11 can be written as, so all Rockville High School basketball players are talented athletes. Yes, just another way of saying it. Venn diagrams can also be used to demonstrate that the argument of example 10 is not valid. To show the invalidity of the argument in example 10, one must show that an object in Q may not lie in circle P. Yeah, you can use this law of detachment to make any statement, either proving or disproving something. Okay, the compound statements known as the conjunction and the disjunction can also be related to the intersection and union of sets. Relationships that can be illustrated by the use of Venn diagrams. For the Venn diagram, we assume that the sets P and Q may have elements in common. Okay, the elements common to P and Q form the intersection of P and Q, which is written P intersection Q, the upside down U. This set, P intersection Q, is the set of all elements in both P and Q. The elements that are in P and Q or in both form the union of P and Q. So there's the union, anything in P and anything in Q, which is written P union Q. This set, P union Q, is the set of elements in P and Q. Yeah, and so from the perspective of conjunction and disjunction, if you're thinking about P and Q as statements, this is like an and statement. So here P is true, but Q is not true. Here Q is true, but P is not true. Here both P and Q are true. So from the statement of a disjunction where either P or Q could be true and the entire statement is true, well, that's P union Q is that statement. The validity of that statement, P union Q. It's if either P or Q or both is true, then the whole statement's true. But a conjunction is only the intersection of those statements where they're both true. If just one is true and the other is not true, then the statement is false.